Math 3, Practice 2A.3.2, the Remainder Theorem. Alright, so remember when we're talking about the Remainder Theorem, okay, we're talking about division of polynomials. And the Remainder Theorem simply tells us when we divide a binomial such as this or this into a polynomial, that the remainder we get determines if it's a factor or not. Okay, and remember, when we mean a factor, we mean like x minus 2, 2x minus 3, okay, that, and it could be more, you know, x plus 1, depending on the degree. But when we get a graph, okay, and actually not that graph, okay, so when we get these factors, the factors are the points on the graph that are the x-intercepts. Okay, we also call them zeros or roots. You'll see that a lot as well. But this remainder theorem tells us about that. And the idea is, if the remainder theorem, so if I divide this into this and I get a remainder of 0, that tells me that that 3 is a 0. It's a factor and a 0. If I get a different number, say I get something like 12, then that tells me that where 12 is, the x value of 3, this x value again, the y value would be 12. So it gives me a point on my graph. So whatever remainder I get is going to tell me something from my graph. Okay? Now, there's two ways to divide polynomials. Okay? Well, technically there's only one way, but there's two ways we can do it. There's the longhand way, or what we call synthetic division, which is basically the same thing but in a shortcut form. Now, it doesn't matter which one you like. For question 1, though, I am going to show you both. Okay? So this would be the long division, longhand way. Okay? When I say long division, I mean long division, just like when you went. Okay? Just division just like that, where you took these numbers, then you subtracted, then you brought down the next term, figured out the next number, and brought the next one down, and then you multiplied, and then you subtracted, and then you just kept bringing stuff, you know, you just kept going like that. That's what we're talking about here. Okay. So this is the idea that we're going with. We're just doing it with polynomials, okay? So the way you set it up with long division, you know, x minus 3, this guy, okay, goes into, and then you write your polynomial. Now, there's something to note about when you write your polynomial. Whatever your highest term is, say it's the 5th, you have to have every single exponent underneath that. Okay? Remember, x to the 0 is usually just the constant number, because x to the 0 is 1. So that's like my x to the 0, x squared, x cubed. I don't have any just x term. So if you don't have one, you consider 0 times that one. Okay? So I'd go plus 0x, then plus 36. Division of polynomials, whether synthetic or long, won't work unless you have every single x term in there. Okay? So if I have x, just x, you know, I'd have 2 terms. If I have x squared, I should have 3 terms. If I have x cubed, I should have 4 terms. Okay, and so on and so forth. Okay, so once again, the idea now is we take a look and we say, okay, I've got two digits here, x and 3. So I'm going to have to go to two terms to do it. So my first number is going to be right here. Okay. Then what you do is you take a look at your x, your leading number, and your leading x, and you say, how can I make them the same? Okay. X cubed, how can an x become an x cubed? Well, we'd have to multiply by x squared. Then we go x squared times x, which is x cubed, which is what we wanted. So I write x cubed here, because I go x squared times x. Then I go x squared times negative 3, and I get a negative 3 x squared. Okay. Then we're going to subtract that. Now, that's what we do, but sometimes some of us have difficulty with subtraction. So my suggestion is change a negative to a positive, positive to a negative, and add. Because it tends to be a little bit easier. But you can just subtract too if you know what you're doing. Just beware when you subtract a negative number from a negative number, you're actually adding a number to it. So when we add them, we get that becomes 0, which is what we want to happen. Okay, if that doesn't become 0, then you made a mistake. Then negative 7x squared plus 3x squared. So negative 7 plus 3, which would be negative 4x squared. Then we bring down our next term, plus 0x, and we do the process all over again. Okay, same process all over again. I look at this x, and I say, how can that x become a negative 4x squared? Okay, how can I get my x to be the same thing? Well, I'd have to times by negative 4 and by an x for it to work, right? So we would then have a negative 4x squared. Oh, not squared, huh? Just x. Okay. Notice that we started out with a cube, but because we're pulling one x out, I mean, think about it. That's x cubed, right? If I divide by one of those x's, we're going to end up with x squared. So your result, I guess, would be 1 less power than what you started out with. Okay, 1 less power than you started out with. Alright, so then I take that negative 4x and I times it by x and I times it by negative 3. So I get negative 4x squared, which is what I wanted, then plus, because a negative times a negative is a positive, 12x. Then once again we say, okay, let's make this a negative 12 and a positive 4x, and let's add them. And then we end up with 0 once again, which is what we wanted. And then 0 plus a negative 12x would be negative 12x. Then I bring down this plus 36, and I do the process one more time. Okay, we're not going to add any other numbers to it, like we sometimes do with regular long division. But we will have a remainder to deal with. So then I look at this x and negative 12x and say, how can these be the same again? Well, I'm going to have to multiply mine by a negative 12. So minus 12. Then I go negative 12 times x to get negative 12x. Okay, hopefully you're seeing that pattern now. Then 12 times 3 to get plus 36. And you should be getting excited now seeing this. Then I say, okay, let's change their signs and add them, or just subtract them. So 36, or negative 12x plus 12x, okay, cancels out and gives us 0, which is what we wanted. Okay, then 36 plus a negative 36 will also give us 0. And that number, whatever it is our remainder. And using the remainder theorem, that tells us something about this graph here, okay, about this equation, this polynomial. In other words, if we graphed this polynomial, okay, we have x minus 3. If we set x minus 3 equal to 0, we get x equals positive 3. The point 3, 0, the x value would be the whatever number's in there, and it's always the opposite, right? Because this would be a factor in parentheses. That's the other thing to realize, is that we've got a factor now. We know that x minus 3 times x squared minus 4x minus 12 would lead us back to this result. Okay? Just like if we take 5 times 10, that equals 50, right? Well, if I go 5 times what will give us 50? We'd divide by 5, right? And we'd figure out that it would be 10. Okay? But that still doesn't change the fact that it's 5 times 10 would equal 50. So over here it's the same idea. That this quadratic, okay, that we found when we divided by this, and we divided it from this one, okay, that these two together multiplied equal this. So one of my factors, okay, when we set it equal to 0, that tells us what our zeros are, our x-intercepts, our roots. Okay, so at a positive 3, 0, our graph goes through that point. Now we could factor this down to try to figure out what it could be. And I think if we factored that with the box method, you'd actually end up with, let's see, x plus 2 x minus 6. Would that work? Let's see. X squared plus 2x minus 6x minus 12. X squared minus 4x minus 12. Yeah. So the next step, which we're not doing, but the next step would be to take this, factor it down, and then I look at this and I can see where my 3 zeros are. Okay? At a negative 2 and at a positive 6, right? Because when it's in parentheses, we always think opposite. Okay? So I've got those 3 zeros, those 3 roots. Because my remainder was 0, that told me that this was a factor. It was an x-intercept. It was a 0, a root. And that's how far we're going. Okay, right now, that's how far we're going. But if we wanted to go further, that would tell us this. Then, using what we learned last time, with a positive, odd degree, I know that my end behavior, as I go to the right, is going up. As I go to the left, is going down. So somehow, my graph is going to look something like that. And it helps me eventually draw that basic shape. Okay? That's essentially what it wants us to do. But for right now, we're just concerned about finding out if our remainder is 0 or a number, and knowing what those factors would then be, right? These guys. Okay? But that's long division. Okay? That's long division. Now, and I made a big mess of this, didn't I? Let me show you synthetic division here. And I like to do it up against long division because I like you to see that the numbers are actually the same. They come from the same place. Yeah. Didn't want to get rid of my beautiful graph I created there. So, for long division, this is how it works. Or synthetic. Okay. So we're just going to focus on the numbers. Okay. We just focus on the numbers. So this number, now with division, whenever we have that x minus 3, we think of this as a positive 3. Okay. And that has to do with those, since it's factors, we're solving for 0, and you'd have to add 3 to get x equal to 3. So if it's x plus 3, we would think of it as a negative 3. Okay? So we've got our 3. That's the number we're dividing by. So we make this little like shelf, and we put our 3 on it, the number we're dividing by. Okay? Then we focus on the numbers that we have here, or probably better yet, right here, the coefficients, because we still have to deal with that x idea. So this one would be 1, so I write 1. This one would be negative 7, so I write negative 7, then 0, and then finally 36. Then I'm going to make this bar down here, and then here's the process. We say, okay, this 1, we don't have anything for it yet, so we pull it down and we put it on the bottom. Then I'm going to say, okay, let's take this 3 and let's multiply. Okay, so 3 times 1 is 3. Then I take that 3 and I place it under the 7. Then I'm going to add those two. Negative 7 plus 3 would give us a negative 4. Okay. Now what I want you to notice is this 1, we see it right here, we see it up here at this coefficient of the x squared. Okay. Then we get a negative 4. Notice we have a negative 4 down here, and to get ours to work for it, we multiply by a negative 4. Okay. To get this, which gets 0, and then you can probably guess what our next number is going to be, because 3 times negative 4 is negative 12. Okay, 0 plus a negative 12 is negative 12. So see, that number shows up right here and right there. Okay, then we go 3 times negative 12, which gives us a negative 36. Then we add those, and we get our remainder of 0. This last term is always, once again, your remainder. And we see it again here. That 0 here, that 0 here. Okay, so it does the same thing, but it's just focused on the coefficients. That's why it's quicker, because we don't have to write it out like this. But we're essentially, as you can see, the numbers doing the same thing. Then the only thing you have to remember is, because we started out with x cubed, this first one is actually x squared. Then the second one would be just the x, and then what comes after that, just the constant. And because there's no remainder, that tells us that these are factors, and that if we multiply them together, that'll get us back to here, but that we can use that to then factor things further. Okay? So, I would suggest using synthetic division, and from here on out that's the only one I'll use because it's quicker, but it does the same thing as the long division. Okay? Alright, so let's look at number 2 now. Okay? So we've got 2x to the 4th. Notice we're missing an x cubed minus 6x squared plus x plus 2. So synthetic division, and we want to divide that by x plus 2. So that's really a negative 2 that we're dividing by. So for synthetic division, I go negative 2, and then I do my coefficients. My first one is 2, then I have to include the x cubed, so that's 0, then negative 6, then positive 8, then 2. Draw my line, and then I start my work. Bring the 2 down. Negative 2 times 2 gives me a negative 4. Add that. 0 plus negative 4 is negative 4. Then multiply negative 4 and negative 2. Give me a positive 8. And you don't have to do all these arrows things. I'm just trying to make sure you know what I'm doing. Okay, and we add those. Negative 6 plus 8. Positive 2. Negative 2 times positive 2 again is negative 4. 8 plus negative 4 would give us a positive 4. Negative 2 times positive 4 gives us a negative 8. Then 2 plus negative 8 is negative 6. Now notice, this is my remainder. Now this one wasn't 0. Okay, this one wasn't 0, it was negative 6. Okay, so when I write that, because I'm trying to find the quotient, so the way I write my answer with the remainder is like this. We started out with x to the 4th, right? So this would be x cubed, so 2x cubed, minus, because it's negative, 4x squared, plus, because it's positive, 2x, plus 4, because it's positive. Now, what do we do with this remainder? Okay, well, in long division, when we had remainders, before we started turning them into decimals, we would have to, it's basically a fraction, right? So what I do, I divide it by x plus 2. So my remainder is negative 6 over x plus 2. and I just tack that on to the end. Okay, so the way I would write my complete answer would be 2x cubed minus 4x squared plus 2x plus 4 plus, or actually minus because it's negative 6, minus 6 over x plus 2, which I can't reduce further, so that's what I end up with. Now, is that ugly? Yeah. That's why we mainly like to use division to find when a remainder is 0. We're usually checking it for factors. Okay. Could I go x plus 2? Yeah. Would that multiply to equal this? Yeah. But it doesn't help me out as much as I want it to. What it does tell me, though, this negative 6 here and this negative 2, it tells me my graph actually goes through the point negative 2, negative 6. That point, my graph is somehow going to go through it. Okay, that's another part of the remainder theorem. If it's not 0, then my graph goes through this point of what we divided by and what we ended up with, that remainder. That's why we like it when it's 0, because that tells us something more important. Okay, those factors are much more important when it comes to helping us out. Alright, and there we go on those two. Now let's hustle through the rest of this, right? Okay, synthetic substitution I think is crap, but it's good practice for the synthetic division, so let's use it. So we've got x equals negative 4, so negative 4 is in our box. We've got a squared, so 3, and x, that would be the next one, 6, then a 10. And then we'd use synthetic division. And we'd go 3, that would give us negative 12, add that would give us negative 6, then that would give us positive 24, add that and we get 34. So with synthetic substitution, all it wants you to tell me is, oh, when x is negative 4, y is 34 in that function. The reason I say it's crap is because of this. Now that wasn't too hard to do on this one, but I could easily use a calculator. If I know what x is and I want the y value or the output, can I just put in my x value into the equation and solve it for the y value? Yeah, okay, we can do that. And so that's why I think it's pretty much crap, okay, is because we can do that and end up with the same exact stuff going on, okay? Now, did I do this right? It's 3 times 16, 48? Yeah. Then why am I not ending up with the right thing? What did I do wrong? Let me do the synthetic division again. Duh, you guys, I didn't even follow order of operations. Come on, people, help me out here. I combine those two when I can't. Okay, so 48 minus 24 would be 24 plus 10 would be 34. See, when you do it correctly, it actually ends up to give you the same thing. Okay, so synthetic substitution sometimes can be a little quicker, especially if you can do it really good, but most of the time I'd say just plug this in for the x values and go from there. But this is a good way to practice synthetic substitution for now. So we start out with x to the 5th, so we've got 1, no x to the 4th, 0, x cubed, 4, no x squared, 0, x 2, and then negative 16. Bring down the 1, we get 2, 2, we get 4, 8, we get 16, 16, we get 32, that gives us 34, so then we get 68, and then we add that, negative 16 plus 68 would be 52, so when my x value is 2, my y value is 52. That's all it wanted you to do on 3 and 4. Okay? Now 5 and 6, for some reason they like to really test you on this stuff and say, well, what if we don't know what one of these is, but we do know what the remainder is? In other words, they're saying, if I've got this 1 here, and I were to use synthetic division or long division, what would this number have to be in order for us to end up with a remainder of 4. So if I bring this down and go 1 times 1, and I get 1, and I get k plus 1, and then times that by 1, now it'll give me a number that when I add it, we end up with that 4. Okay? So, instead of just trying to guess, there's an easier way to do this. Basically, it's the idea that this is like the y value when this is the x. So 1, 4 would be my point. So taking my equation, I know if I plug in 1 for x, it's going to be equal to 4. Okay? So then we just simplify. 1 plus k plus 10 equals 4. 11 plus k, because 1 and 10 combine, because they're on the same side. Subtract 11, and we get k has to equal negative 7 for this to work. Okay? That's all they wanted you to do. Okay? So we look at number 6, same idea. Okay? So except it's negative 6, so when x is negative 6, our y is 9. So plugging it in, we get 9 equals negative 6 squared plus 5 times negative 6 plus k. So that would be 36 equals 9 minus 30 plus k. 36 minus 30 would be 6 plus k equals 9. Subtract 6. So 3 would have to be equal to k. Alright. Now the rest ones, they're just giving us story problems, but they essentially want us to divide these all. Okay, the area in square feet of a rectangle garden can be expressed as a product, or the area. So we've got one, area is width times length equals area. So if we have one and we're finding the others, we just divide. That's all they're saying. So plus 2, so synthetic division, that's negative 2. Then I have 3, 13, and 14. So I do synthetic division. This times is negative 6, add these, it's 7. This times is negative 14, add these, it's 0. So we started with x squared, so we get 3x plus 7. That's what our length would be. Okay, 8, same idea, we're dealing with areas, so we just do the same exact thing. Negative 4 means we've got a positive 4 here. 7 squared, 34x, negative 24. We just multiply, bring down the 7, gives us 28, add that. That would give us a negative 6. That gives us negative 24. Add that, that would be a negative 48. Okay, so the width of our patio is a little bit uglier. Be 7x minus 6. Okay, I didn't screw that up, right? Nope. Minus 48 over x minus 4. A little uglier. Okay, number 9, same concept. Okay. Well, hold on, maybe not. Nope, I lied, it's still dividing. So plus 4 means our number up here is negative 4, right? We always do the opposite. Then we have 0.5, and then 8, and then 24, and then we'd say 0 because we need that last term. So bring it down, 0.5. Negative 4 times 0.5 is negative 2. Add that, that would be 6. Then negative 24. Add that, that would be 0. And then that would be 0 as well. So basically we just end up with 0.5t squared plus 6t, which is alright to have. Okay, now the last one. So I don't have much time to do this one, so plus 4 again, so we have negative 4, 0.2, 8.8, 32, and then 0. Bring down 0.2, then negative 4 times 0.2 is negative 0.8. Add those, we'd get 8. Negative 4 times 8, negative 32, gives us 0, and then zeros again. So my result would be 0.2t squared plus 8t, and boom. See how quick synthetic division can be if you know what you're doing? So there we go, guys.